Introductory Neuroscience and Neuroinstrumentation, the first lecture on the action potential. Hello, in this session we will examine the ionic basis of the action potential in excitable cells, specifically neuronal cells. There are other excitable cells in the body, electrically excitable, muscle cells, cardiac cells, but we are talking about neuronal cells. Okay, so the background. So we learnt in the previous lectures that the resting membrane potential of a cell is about minus 60 millivolts in the squid giant axon, and it can be even lower than that in mammalian neurons. So the resting membrane potential V subscript M, when it changes from minus 60 to minus 55, that is depolarization happens, the nerve gets excited. Now it has to reach a threshold. So the threshold is about 15 to 20 millivolts, and with that you get a spike of 100 millivolts, and it lasts for about 1 millisecond approximately. So this is the action potential, and the first thing is it's all or nothing. So when the membrane threshold is reached, then you have the spike. It's invariant, and the information is coded in the frequency, number of spikes which occur. It's not coded in its shape or form. Okay, so this is the critical point to note, that the information of an action potential is coded in its frequency, and it's all or nothing. So it occurs when the membrane potential reaches the threshold, right? So in 1938, Cole and Curtis showed, this is in Marine Biological Laboratory in Woods Hole in Massachusetts, they showed that during the action potential, the membrane permeability or its conductance to various ions increases 40 times from normal. So subsequently, the next year, Hodgkin and Huxley showed that the membrane potential changes from minus 60 millivolts to plus 40, nearly 100 millivolt change during the upstroke of the potential. So on the right, you see the impedance change of during an action potential. So the action potential is the thick black line, and it's superimposed on the impedance data, which is the gray band. And you see during the time course of the action potential, the gray band increases substantially, and then it comes back to normal. This widening of this impedance band reflects the change in the membrane resistance from 1000 ohms per square centimeter. It drops to 25 ohms per square centimeter. Please note that the membrane capacitance doesn't change. It's a passive property. It depends on the phospholipid layer, so that does not change. Okay? Now, how do you measure impedance? Now, if you remember from your high school, there is a concept of the Wheatstone bridge, where you have 4 resistors and they're all balanced, and when they're balanced, the central galvanometer is at 0. So one of the arms of the Wheatstone bridge is the impedance measurement from the squid. So that tells us what the impedance changes are. Okay, so how do we explain these impedance changes? I mean, what happens? Because it comes back to baseline. So these can be explained if the selective permeability to sodium is reversed, for a brief period. That is, sodium penetrates much faster than potassium. Okay, this sodium influx, causes the intracellular compartment to become positive briefly with respect to the extracellular environment, right? So looking at their actual data, and some of their data is still unrivaled in its clarity and clearness. You see traces, So trace 1 and 3 is the action potential of the squid giant axon in normal seawater. In 2, the sodium outside, 1/3 of it has been replaced with isotonic dextrose, and you see the action potential is much smaller. 3 is when you replace it back, and then it comes back to normal. So when the extracellular sodium is lowered, the action potential becomes smaller, and when it's totally sodium free, then there are no action potentials. So the action potential, the initial part of it, is completely sodium ion dependent, right? So how did they prove it, that it actually is from the membrane? Okay. So this was referred to in an earlier lecture. So you take the squid giant axon and you actually have a small roller and you roll out the cytoplasm inside and then you reperfuse it with whatever solution you want. It has to be a potassium solution and it doesn't really matter. It could be any potassium solution as long as the pH is around 7.5. So you can replace the intercellular fluid with a solution of potassium sulfate, and the action potentials look practically the same as it were with regular intracellular contents. So on the right you see their data where the top figure is action potentials from a squid axon perfused with potassium sulfate, and below are action potentials from the intact squid giant axon. Neuronal membranes can be represented as an electrical circuit. All you engineers would understand this. It was proposed by Hodgkin and Huxley in the 50s, and here C subscript M is the capacitance of the nerve membrane. Usually it's put at 1 microfarad per square centimeter. In the middle is the diagram of an excitable membrane of a nerve fiber. So Cm is the capacitance, Rna is with its battery below is the sodium channel, R subscript K, the resistance subscript potassium, is the potassium channel, and these are the main conductances. And you also have an R leak, where which is a small conductance where things, it's not a perfect compartment, so things keep leaking out and there will be a small potential due to that. So the conducting pathways, besides the capacitance, they are represented by parallel channels, because in the membrane, with the phospholipid membrane, you have sodium channels, you have potassium channels. So each of these channels has a battery and a resistance. The battery is the electromotive force which pushes the ion into or outside the cell. So at rest, the resistance for sodium is high. Okay. That means it's reciprocal, which we actually use rather than resistance, which is G, denoted by G, which is the conductance, is low compared to potassium. So let us analyze some electrical changes in axons during activity. First, to recap, the resting membrane potential of an axon is permeable to sodium but not solely permeable to, the resting membrane potential of axon is not solely permeable to potassium, it is not totally impermeable to sodium, and it's also permeable to chloride. So the potential across such a membrane is given by the GHK field equation, where P is the permeability coefficient of each ion, okay, or the conductance. So if you look at the equation, we went through it in an earlier lecture. Instead of just potassium, which is give us only the potassium ion effects, we also add in sodium and chloride, and we call it a constant field equation because we assume that within the phospholipid membrane the potential is constant. So when you put all these things inside, then you get a realistic value of the resting membrane potential. So when the nerve membrane is depolarized by an outward flow of current, so it becomes less negative inside, sodium permeability, or G subscript Na, rises immediately, and sodium ions rush into the cell because of the concentration gradient. If you remember, outside it's seawater, sodium is about 150, inside is about 18 to 20. So it's a huge rush, water rushing in, over a concentration gradient. So instead of water falling from a height, you think of sodium ions. So how does this occur? How does it depolarize? So it can occur in two ways. You can cause an outward current by applying a cathode, or the adjacent segment or area has an action potential, and that action potential invades this segment and causes depolarization. So once sodium enters, it lowers the membrane potential and causes further depolarization. And then there's an explosive acceleration of sodium entry, and that is the rising phase of the action potential. The cell inside becomes positive. it really reaches the equilibrium potential for sodium. If you remember, it's about plus 60 millivolts. And if you see on the right, you have the action potential, you have the intracellular electrode, and that's in the squid giant axon. So then what happens is the net, once it reaches the peak, the net inward movement of sodium becomes 0, and that's the peak. So the conductance of sodium stops and sodium permeability falls. This is called sodium inactivation, and it reaches baseline in about 1 to 1.5 milliseconds. So what happens with potassium? So at the peak of the spike, the potassium conductance rises, not with the sodium, but a little delayed. It peaks about half a millisecond later and returns to normal in 3 milliseconds. After generation of the action potential, the membrane potential repolarizes, becomes more negative, and it goes below 0. So here it comes down and then it goes below 0. So this is called hyperpolarization. It's gone below 0. This is depolarization, this is coming back to normal, and this is hyperpolarization. And it's also called an after hyperpolarization because it occurs after the action potential. Now please bear in mind that a neuron can fire 60,000 to 90,000 times before it fatigues. So it is very, very efficient compared to all electronic devices, and there is a lot of redundancy built in. There's a huge safety margin. It fires because it loses energy, and the energy has to be made up with the ATP, phosphate transfer. But 60 to 90,000 times, it's good to go. So now coming to the voltage clamp, we can measure from inside the cell, no problem. Why do we need to clamp the voltage? So we do it to simplify the analysis. With the voltage clamp, we can measure current flow in a patch of membrane whose voltage 1 is maintained at a set level. It's called the command voltage, or it can be changed stepwise using a feedback amplifier. So you see the circuit on the right. You have a squid, you have a current passing electrode, and then you have a signal generator with a command voltage, and this is the kind of circuit which is used. We'll get into details subsequently. So what is the advantage of the voltage clamp? So remember, there are potassium things happening, the sodium things happening, voltages are happening, and current is happening. So this technique dissociates voltages and currents. So we can hold the voltage constant and see what the current is, or we can current clamp it and see what the voltage is. So these techniques were developed by Kenneth Cole at MBL in Massachusetts, and quickly they were used by Hodgkin and Huxley in Plymouth, in Cambridge, and they figured out the action potential with this technique. So consider the circuit on the right. You have the axon, you have a current electrode, and you have a voltage electrode. So the idea is you keep the voltage constant and you see how much current passes at that particular voltage. Okay, and you not only the amplitude but also the time course. So in the two electrode, the classic voltage clamp technique, one electrode measures the voltage across the membrane while the other injects the current to keep the voltage constant. So the experimenter sets up the voltage where the axon should be held. This is the command potential. So current is then injected into the cell in proportion to the difference, the delta, between the present membrane potential and the command potential. This occurs continuously, therefore clamping the membrane potential to the command potential. So by measuring the amount of current injected to hold it at the command potential, we can determine the amplitude as well as the time course of ionic currents flowing across the membrane. So the advantages: the current injected into the axon is equal to the current flowing through the ionic channels of the membrane. Remember, current in membranes is not electrons but ions, and therefore you get a direct measurement of this current at the particular voltage. So ionic currents, sodium, potassium, are both voltage and time dependent. they become active at certain membrane potentials and do so at a particular rate. So keeping the voltage constant of the voltage clamp allows these two variables to be separated. The voltage dependence and kinetics of these ionic currents can therefore be measured directly. Okay? This was not possible before, this technique. So thank you, and in the next session we will consider more details of the action potential.